Good afternoon. This is, or good evening or good morning. This is a video on basis of energy. So by this time, oops, sorry. By this time you should have started or clicked to this particular page. The study of energy is called thermodynamics. Thermo meaning heat or energy. Dynamics meaning movement. There are three laws. The first law of thermodynamics is the same as the law of conservation of energy. And you can read that. So basically what it says is, the first law says, all the energy must be accounted for. It is not lost. It's just moved from one thing to the next. The interesting thing about energy is you cannot measure it unless it's moving. There are different types of units of energy. One is the one that I will use, which is calories, and it's not the metric system unit. The definition is the amount of energy needed to raise 1 gram of water by 1 degree C. And the thing why it's not the metric system unit is it's only at 4 degrees C is this value actually 1.00 calories. If it's at a different temperature, you have different numbers, but they're really different. They're really the same. So if you're not at 4 degrees C, maybe it's 0.9997. So we'll call it 1 all the time. Or the unit that the metric system uses is joules. I have no real good explanation for the definition of joules because it doesn't mean anything to me. But calorie does. It's how much energy I need to put in to raise 1 gram of water by 1 degree C. I can see that. Whereas joules is not as easy to see. So I like to use the conversion factor. 4.18 joules is equal to 1 calorie. There is another energy unit called the BTU, a British thermal unit. It's an English system, so we don't use it as much anymore, but you see it sometimes in products. Specifically, like air conditioners can be rated in BTUs. We won't use that number of calculations at all. So we use calories most of the time and joules some of the time. There are two in general, and the problem is with energy, you're going to see that people talk about energy in different perspectives. The most common perspective is kinetic and potential. Kinetic energy is the energy of movement. There's an equation. And the other type of energy is potential energy, or stored energy. And there's a lot more examples of potential energy. People talk about a lot more. One, of course, is chemical energy, the energy that the base particles are the atoms that make up, or the material that makes up the base particles are being held together with a certain amount of energy. That's chemical energy. Another one is positional potential energy. That's why a chairlift works on a ski slope. You need to get to the top. That requires energy, and then when you come down, you're using the energy. And that's a good example of how potential and kinetic energy balance off each other. As you go down, you speed up. Your kinetic energy is increasing while your potential energy decreases. And that's how potential and kinetic energy flow between each other. That's not as much what we're going to do when we deal with energy. The second law of thermodynamics, and this is not the second law of thermodynamics, it's just one of the explanations that come from the second law, is how does energy flow? And the rule is that energy always flows from a higher temperature body to a lower temperature body until the temperatures are equal. Therefore, the question that becomes, what's temperature? Temperature and energy or heat are not the same thing. Heat is a form of energy, which is the total amount of it. Talking about total amount of energy. Temperature is and you have to memorize this, the average kinetic energy of all the particles in the substance. Which means, unlike what one would think, if you have a cup at a certain temperature, or a liquid at a certain temperature, not all the particles in that liquid have the same kinetic energy, which is weird. That's not, you wouldn't think that, but that's how it works. Some will have more, some will have less. There are two types of temperature scales, relative and absolute. The difference is, relative temperature scale, the basis of the scale can change in the universe. For example, Celsius and Fahrenheit are based on the same thing, freezing point and boiling point of water, which can change in the Earth. Go high up, the boiling point decreases. Whereas the absolute temperatures change, the basis does not change, and that's absolute zero. You can tell this, in the example is Kelvin, you can tell this because of the degree sign. A degree sign indicates it's a relative temperature scale. Absolute temperature scales do not have a degree sign. I give you the conversion of Celsius to Kelvin. That's the user one. The third law is a little bit harder to explain, and it's used a lot in other things in thermodynamics. But what it is the condition where there is no energy. To have no energy, which is called absolute zero, you have to have two things. You have to be at the temperature of 0 K, no energy due to movement, plus you have to have what they call a perfect crystal. And the reason is, in a perfect crystal, that's a substance that has only one particle type. And you need this because if you have multiple particle types, the dissimilar particle creates what they call randomness or disorder, which in thermodynamics is called entropy. And since you see disorder requires energy to happen. So you can't be at the condition of no energy, absolute zero. So you must have a substance that has all the same material. So once you have that substance with all one type of material, there is no energy of randomness, or there is no entropy energy. So then you take it down to 0 K, and you do not have energy with respect to motion. Besides entropy, the other energy, the energy due to motion and the energy due to the particles hanging on to each other and due to the energy in a phase, that all has a name that's not entropy. It's called enthalpy, which is delta H. Entropy is delta S. Sometimes we call enthalpy heat, or even sometimes potential energy. Those two names, entropy and enthalpy, is another perspective to energy that's a little bit different than kinetic and potential energy. But that's the third energy, and that's the only thing. So what's the third law of thermodynamics basically saying is, if you're not at absolute zero, which we've never gotten to, everything has energy in it. Everything has energy in it. And that's why the Kelvin system, there's only one basis, which is absolute zero, and you can't change it, because everything has energy in it. What the actual second law of thermodynamics says is, you're not responsible for this, is that the entropy of the universe is always increasing, which means that everything goes to disorder or randomness unless you put energy in. If you put energy in, you can create you can create the order, and you can get rid of disorder. But it doesn't happen naturally. Nature always goes to disorder. That's what the second law says. Thank you.